The Elegant Universe by Brian Greene. Picture this. The two greatest achievements of modern science are locked in a bitter feud, and most of us have no idea it's even happening. In one corner, we have Albert Einstein's crowning achievement, general relativity. It's this beautiful, sweeping theory that explains the universe at its grandest scale. Planets gliding through space, galaxies spiraling majestically, the very fabric of space and time bending and flexing like a cosmic trampoline. And it works flawlessly. In the other corner stands quantum mechanics, this wild, utterly bizarre theory that governs the tiniest realms of existence. It's all about atoms and the subatomic particles dancing inside them, operating on probability, uncertainty, and what can only be described as microscopic pandemonium. And guess what? It also works perfectly. Here's the problem that's been haunting physics for over 50 years. When you try to merge these two flawless theories, everything falls apart. They contradict each other spectacularly. The mathematics collapses, spitting out absurdities like infinity. They simply cannot both be correct. This isn't just some ivory tower problem. It means we're completely in the dark about what happens in the universe's most extreme environments. What's really going on at a black hole's heart? What actually occurred in that first explosive instant of the Big Bang? Our understanding of reality has a fundamental crack running through it. But what if one idea, elegantly simple yet mind-bendingly profound, could heal this fracture? What if it could weave these two magnificent theories into one seamless tapestry? This is the adventure Brian Greene takes us on in his breathtaking book, The Elegant Universe. Greene isn't just a brilliant physicist, he's a gifted storyteller who guides us to the very frontier of human understanding. He unveils a revolutionary concept that might just be the Holy Grail, the theory of everything that Einstein chased but never caught. Here's what I promise you. By the end of this journey, you'll grasp this fundamental conflict tearing at the heart of physics. You'll discover how one beautifully elegant idea, that everything from the tiniest quark to the most distant quasar, is actually made of infinitesimal, vibrating strands of energy, might be the answer we've been seeking. You'll start seeing the universe not as a random collection of disconnected bits, but as one magnificent, cosmic symphony playing out across space and time. Let's start where many great physics stories begin, with a teenage Albert Einstein lying awake at night, pondering a deceptively simple question. What would happen if you could race after a beam of light and actually catch up to it? Common sense, backed by Isaac Newton's physics that had ruled for 2 centuries, suggested the light should appear frozen in front of you, standing completely still. But there was a problem. James Clerk Maxwell's equations describing electricity and magnetism told a completely different story. They insisted light always travels at light speed, never slowing down, never stopping, regardless of who's observing it or how fast they're moving. Both couldn't be right. Something had to give. This paradox gnawed at Einstein for a decade. Then, in 1905, while working his day job as a clerk in the Swiss Patent Office, inspiration struck. Newton and our everyday intuition were simply wrong. This revelation became special relativity, and it completely rewrote the rules governing space and time. Let me paint you a picture. Imagine 2 leaders from warring nations sitting on a train, ready to sign a historic peace treaty. They're positioned at opposite ends of a long table. To ensure perfect simultaneity, a light bulb is mounted at the table's exact center. When it flashes, light rushes outward in both directions, reaching both leaders at precisely the same moment. They see the flash. They sign. Everyone aboard the train witnesses simultaneous signing. Peace is declared. But now shift your perspective. You're standing on the platform, watching this ceremony as the train rushes past. From where you stand, something curious happens. The leader facing the train's direction of travel is moving toward one light beam, while the other leader is retreating from their beam. So from your vantage point, light has less distance to cover to reach the first leader and more distance to reach the second. Since light speed remains constant for everyone, whether you're on the platform or riding the train, you reach an unavoidable conclusion. The first leader signed before the second one did. So who's actually right, you on the platform or the passengers on the train? Einstein's brilliant insight: you're both right. The very concept of simultaneity, of events happening at the same instant, isn't absolute. It's relative, depending entirely on how you're moving. Two events that appear simultaneous to one observer might be separated in time for another. This was just the opening act. Special relativity revealed that time itself isn't some rigid universal clock ticking identically for everyone. The faster you move through space, the slower you move through time. Einstein imagined a light clock where a single photon bounces between two mirrors, each round trip marking one tick. When the clock sits still, the photon simply travels up and down. Simple enough. But set that clock in motion, and from our perspective, the photon must travel a longer diagonal path to keep up. Since light's speed is constant and the path is longer, each tick takes more time. The moving clock literally runs slower. And this isn't some quirk of clock mechanics. It's time itself that's malleable. Astronauts traveling near light speed would age mere months while years passed on Earth. Time bends. Space contracts. Objects in motion physically shrink in their direction of travel. Einstein had merged space and time into a single, four-dimensional fabric, space-time. How we slice this fabric into separate, space, and time depends entirely on our motion through it. He'd resolved the first great conflict. But in solving one problem, he'd created another. Special relativity established a cosmic speed limit. Nothing can exceed light speed. Yet Newton's gravity, the reigning theory of its day, flagrantly violated this rule. According to Newton, gravity acted instantaneously. If the sun suddenly vanished, Earth would immediately fly out of orbit. But the sun sits 93 million miles away. Its light takes 8 minutes to reach us. How could gravity's influence be instantaneous? Once again, physics was at war with itself. Einstein knew one theory had to be wrong, and he was betting against Newton. For the next decade, he embarked on an obsessive, sometimes tormented quest to understand gravity's true nature. The breakthrough emerged from what he called his happiest thought. Picture yourself in an elevator when suddenly the cable snaps. You and everything around you begins plummeting downward. In that terrifying moment, you'd be weightless. Drop your wallet and it would simply float beside you. Inside that falling elevator, gravity would seem to disappear completely. Now imagine you're an astronaut floating in a rocket ship deep in space, far from any celestial body, no gravity, you're weightless. But then the engines fire and the rocket accelerates. Suddenly you're pressed against the floor. Drop your wallet now and it falls, just like it would on Earth. From inside your windowless ship, you'd have absolutely no way to distinguish whether you're sitting on Earth feeling gravity's pull or accelerating through empty space. This was Einstein's profound realization. Gravity's effects and acceleration's effects are indistinguishable. This is the equivalence principle. This insight was the key he needed. It connected gravity to motion, and he already knew from special relativity that motion warps space and time. A radical thought began forming. What if gravity isn't a force at all? He pictured a spinning merry-go-round. If you measure its radius and circumference, something strange emerges. Measuring the radius, your ruler points inward, unaffected by the spin, so its length stays true. But measuring the circumference along the moving edge, special relativity says your ruler contracts. A shorter ruler means more measurements to cover the full distance, so the circumference appears longer than high school geometry predicts. The familiar rules of flat, Euclidean geometry break down on that spinning platform. The surface is, in essence, warped. Einstein made his monumental leap. What if gravity works exactly like this? What if massive objects don't exert a force, but instead warp and curve the space-time fabric around them? Imagine space-time as a giant stretched rubber sheet. Place a bowling ball in the center and the sheet sags, creating a depression. That curve is gravity. Roll a marble nearby and it won't travel straight. It follows the curve created by the bowling ball, orbiting around it. That's what Earth is doing. It's not being pulled by the sun. It's simply following the straightest possible path through the curved space-time the sun's mass creates. This was general relativity, a theory not of forces but of geometry. It resolved the conflict with special relativity because these space-time warps don't propagate instantaneously. They ripple outward at light speed, as gravitational waves. Einstein had done the impossible. He'd rewritten cosmic law twice. He'd proven that space and time aren't a static stage for the universe's drama. They're dynamic, active participants in the performance itself. Yet even as he was completing this masterpiece for the very large, another revolution was brewing, a revolution in the realm of the very, very small. And this new world was about to expose a conflict deeper and more troubling than anything he'd faced before. This was the quantum realm. And it was profoundly, unsettlingly weird. The quantum story begins with something as mundane as a hot oven. Late 1800s, physicists tried calculating the energy of radiation inside a heated oven and got a ludicrous answer. Infinity. Something was fundamentally broken in their understanding of energy and light. In 1900, German physicist Max Planck made a radical, almost desperate guess. He proposed that energy doesn't flow smoothly and continuously. It comes in discrete packets, tiny chunks he called quanta. Like money exists in distinct units of pennies or dollars, energy existed in discrete lumps. The size of these energy packets related directly to the light wave's frequency. This simple idea eliminated the infinity problem, but nobody, not even Planck himself, understood what it really meant. Then, in 1905, the same miraculous year he published Special Relativity, Einstein grabbed Planck's idea and ran with it. He suggested light itself isn't a wave, as everyone had believed for a century. It's a stream of these tiny energy packets, particles of light we now call photons. This beautifully explained a puzzling phenomenon called the photoelectric effect. But it seemed to contradict a century of experiments that had proven light was a wave. The definitive experiment was the double-slit setup. Imagine a barrier with two thin, parallel slits cut into it. Shine light at this barrier, and observe what appears on a screen behind it. If light were particles, like tiny pellets, you'd expect two bright bands aligned with each slit. That's not what happens. You see multiple bright and dark bands, an interference pattern. This occurs when waves overlap. Where two wave peaks meet, they amplify each other, creating brightness. Where a peak meets a trough, they cancel out, creating darkness. This experiment seemed to settle it definitively. Light is a wave. So which is it? Wave, or particle? The quantum world's answer is a breathtaking, mind-bending both. Here's where things get truly bizarre. Turn down your light source until you're firing just one photon at a time. You'd expect the interference pattern to vanish. Each individual photon should pass through either the left slit or the right slit. Nothing to interfere with, right? But run the experiment, firing single photons every few seconds, and watch the results accumulate on your screen. The interference pattern reappears, building up dot by individual dot. Somehow, each solitary photon seems to know about both slits simultaneously. It's as if the photon passes through both slits at once, interferes with itself, then lands on the screen at a position determined by that self-interference. This is wave-particle duality. At microscopic scales, things aren't simply one or the other, they're fundamentally both. And it's not just light. In the 1920s, French Prince Louis de Broglie proposed that matter itself, things like electrons, which we think of as tiny solid particles, should also exhibit wave-like behavior. Experiments quickly proved him right. Firing electrons at a double-slit barrier produced the same interference pattern. Everything, it seemed, possessed this dual nature. But waves of what exactly? What's actually waving? The answer from physicist Max Born is one of reality's deepest and strangest features. It's a wave of probability. The wave doesn't tell you where the electron is. It tells you where the electron is likely to be found. Where the wave is large, there's high probability of finding the electron. Where it's small, low probability. This drove Einstein absolutely mad. God does not play dice with the universe, he famously protested. He believed probability merely reflected our ignorance, that some deeper, deterministic reality existed beneath it all. But experiment after experiment has proven that on this point, Einstein was wrong. The universe at its most fundamental level genuinely runs on chance. We can't say an electron occupies a specific position while moving at a specific speed. The very act of measuring its position with perfect accuracy renders its velocity completely uncertain, and vice versa. This is Heisenberg's uncertainty principle. It's not a limitation of our measuring tools. It's a fundamental law woven into reality's fabric. The microscopic world, then, isn't calm and clockwork-like. It's a frantic, chaotic, roiling sea of uncertainty. Even in completely empty space, the uncertainty principle says energy can fluctuate wildly for infinitesimal fractions of a second. Particle-antiparticle pairs spontaneously erupt from nothingness, only to annihilate each other moments later. Physicists call this seething microscopic chaos, quantum foam. And now we arrive at the ultimate showdown, the problem that stood as modern physics' central challenge for over half a century. Einstein's general relativity, governing the very large, describes spacetime as a smooth, gently curving surface, like rolling hills under a peaceful sky. Quantum mechanics, ruling the very small, insists that if you zoom in on that spacetime fabric, down to the tiniest conceivable scales, it's not smooth at all. It's a violent, turbulent, frothing foam of quantum uncertainty. The two theories exist in complete opposition. General relativity's equations require a smooth stage for the cosmic drama. Quantum mechanics tears that stage to shreds. When you attempt combining both theories, equations to describe situations needing both, like the Big Bang or a black hole's heart, they collapse spectacularly. They produce infinities. They generate nonsense. For decades, this impasse stood firm. Physics' two pillars existed in stark contradiction. What was desperately needed was a fresh idea, a new revolution. And it emerged from the most unexpected place. not from a new symmetry principle or a novel insight into spacetime's nature. It came from a simple perspective shift, from a point to a line. What if the universe's fundamental constituents aren't zero-dimensional points? What if they're tiny one-dimensional loops of energy? What if they're strings? This is superstring theory's core insight. Think of a violin string. It can vibrate in different patterns, each pattern producing a distinct musical note. String theory proposes that the elementary particles we observe are simply different notes played by these fundamental strings. A string vibrating one way might appear as an electron. Vibrating differently, it becomes an up quark. Yet another pattern might manifest as a photon. There are infinite possible vibrational patterns, infinite possible notes. This explains the bewildering particle zoo of the Standard Model. But here's the kicker. Among these vibrations, one pattern perfectly matches the properties of the graviton, the hypothetical particle carrying gravitational force. For the first time ever, gravity isn't bolted on as an afterthought. It's an essential part of the cosmic music. The universe, through this lens, becomes a cosmic symphony. All the rich diversity we observe in reality, every different particle and force, is just different melodies played on one single, fundamental instrument, a tiny, vibrating string. This is ultimate unification. Matter and force are two faces of the same coin. They're all just different notes in the cosmic song. But does this elegant idea actually solve the great conflict? It does, and the reason is wonderfully straightforward. A string isn't a point. It's an extended object with actual size, incredibly tiny, but not zero. This means it can't probe the universe down to arbitrarily small distances. All the problems between general relativity and quantum mechanics emerge at sub-Planck scales, deep in the quantum foam's chaotic heart. But a string is too large to see that foam. Like a finger gliding across granite, it's too big to detect microscopic bumps and grains. It smears out the microscopic chaos, smoothing over the violent quantum jitters that would destroy Einstein's theory. By replacing point particles with strings, the conflict simply dissolves. General relativity and quantum mechanics finally coexist in harmony, like instruments in an orchestra. But this elegant solution brings a few startling consequences of its own. First, string theory's mathematics doesn't work in our familiar three spatial dimensions. The theory gets plagued by inconsistencies, bizarre things like negative probabilities, unless the strings can vibrate in more directions. The math demands the universe possess 9 spatial dimensions plus one of time, totaling 10 spacetime dimensions. Where are these extra 6 dimensions hiding? The theory proposes they're curled up incredibly small at every single point in our familiar space. Imagine a garden hose. From far away, it looks like a one-dimensional line. An ant crawling on it can only move forward or backward. But look closely and you discover a second dimension, the circular girth wrapped around the hose. The ant can walk along the hose's length or circle around its circumference. String theory suggests our universe works similarly. It has 3 large, extended dimensions we can see and move through. But at every single point in that space exists a tiny, curled-up, 6-dimensional shape so microscopically small, billions upon billions of times smaller than an atom, that we've never detected it. And here's the most profound part. These hidden dimensions, geometry, isn't just some incidental detail. It dictates the strings, music. The precise shape of these curled-up dimensions determines which vibrational patterns are possible. And since vibrational patterns determine elementary particle properties, their masses, their charges, their very nature, the seemingly random values we observe in our world are actually reflections of these hidden dimensions, intricate geometry. The laws of physics, in a very real sense, emerge from geometry itself. So here's the grand picture. Our universe is a 10-dimensional place. 3 of those dimensions expanded to cosmic scale, forming the observable universe. The other 6 remained tiny, curled up into an intricate shape called a Calabi-Yau space. Within this 10-dimensional stage, everything is made of tiny vibrating strings. The notes they can play are determined by the extra dimensions, shape, and the symphony of all these vibrating strings is our entire universe. Now this story is still being written. Physicists discovered there weren't just 1, but 5 different versions of string theory. For a while, this was deeply embarrassing. The ultimate theory should be unique, not come in 5 flavors. But during the mid-1990s, second superstring revolution, researchers realized these 5 theories are actually 5 different perspectives on one single, deeper theory. A theory living in 11 space-time dimensions. This mysterious overarching framework is called M-theory. Nobody knows exactly what the M represents. Maybe mother, maybe mystery, maybe membrane. Because we've learned that in this deeper theory, strings aren't the only fundamental objects. There are also 2-dimensional vibrating membranes, 3-dimensional blobs, and objects of even higher dimensions. M-theory represents the new frontier. It has unified all previous string theories into one grand, interconnected web. It's revealed a universe richer and stranger than we ever imagined. The quest now is to understand M-theory itself, to discover the fundamental principle from which everything springs, to calculate which of thousands of possible Calabi-Yau shapes describes our actual universe, and finally, to make testable predictions that can determine if this beautiful, elegant story is reality's true narrative. When you step back and really absorb the elegant universe's story, it's nearly impossible not to feel profound awe. This isn't merely a book about physics. It's a testament to the relentless human drive to understand, to discover a single, coherent narrative explaining everything around us, from the smallest speck to the grandest cosmic sweep. What Brian Greene accomplishes so masterfully is showing us that the universe at its deepest level might be profoundly simple. Not easy to understand, but fundamentally simple. The idea that everything we observe, distant starlight, the chair supporting you, even the thoughts flickering through your mind, could all arise from different vibrations of one single entity is among the most powerful and beautiful concepts ever conceived. It's the ultimate reductionism, yet simultaneously the ultimate holism. It reveals that everything connects, everything participates in the same cosmic song. For me, this journey's most powerful lesson isn't about extra dimensions or supersymmetry. It's about the courage to question the obvious. For millennia, we knew there were 3 dimensions. We knew time was absolute and unchanging. We knew particles were indivisible points. String theory teaches us humility, reminding us that our everyday experience provides only a limited window onto reality. The deepest truths often hide in places our intuition would never think to explore. So how can we bring these grand, cosmic insights into our everyday lives? First, try adopting the physicist's habit of questioning your assumptions. Identify a long-held belief about yourself, your abilities, or the world around you. Ask yourself, what if this is just the view, from far away, like perceiving the garden hose as one-dimensional? What if hidden dimensions exist in this situation or within yourself that you simply haven't noticed yet? The biggest breakthroughs often come not from discovering new answers, but from asking new questions. Second, embrace elegance through simplicity. Physics aims to explain the maximum with the minimum, to find one simple principle underlying the complex world we observe. we can apply this in our own lives. Where can you identify the simple, fundamental action that, practiced consistently, would create a cascade of positive changes? Instead of juggling 100 different things, what's the vibrating string that creates your life's music? Finally, allow yourself moments of genuine wonder. Next time you gaze at the night sky, don't just see distant points of light. Try imagining the vast, 10-dimensional space-time fabric rippling with the Big Bang's echoes. Picture the tiny, curled-up Calabi-Yau shapes at every point in space, with reality strings vibrating within them, playing their cosmic symphony. The universe is vastly grander, stranger, and more beautiful than our senses can possibly perceive. This book reminds us that the greatest adventure is the one we take with our minds. That was a summary of The Elegant Universe by Brian Greene. We've explored the core ideas today, but I need to be honest with you. Listening to me talk about this book is like hearing someone describe a beautiful symphony. You grasp the structure, you understand the themes, but you can't feel it. The real magic happens when you experience the book yourself. It's in those moments when Greene's analogies suddenly click, when a complex idea crystallizes into clarity, that this story's true wonder strikes you. This summary is your map, but the treasure lies in the book itself. If anything we've discussed today has sparked your curiosity, I genuinely encourage you to pick up a copy. Reading it isn't just about learning physics. It's an experience that can authentically transform how you see the universe and your place within it. Also, if you found this journey valuable, please take a moment to like this video and subscribe to the channel. It's the best way to show me these explorations matter to you, and it ensures you won't miss our next dive into another transformative book. Let's keep learning and keep wondering together.